All right, welcome back, everybody. Today we are doing some bit of harder problems. We're talking about force between two parallel wires. Okay, so two parallel wires carry current, exert a force on each other. So that's the first thing. Okay, so what we're gonna know, what we should know from the future or in the past, is that with the wire that has a current in it, it's gonna exert a magnetic field. What we also know is that magnetic field can exert a force on a current. So there's like this kind of relationship where current's creating a magnetic field. That magnetic field can also create a force on that current. And that's what's happening here. Okay, so each wire generates a magnetic field that affects the other wire. The magnetic field created by wire 1 at the location of wire 2 is perpendicular to the wire two's current. Okay, let me explain a little bit what that means. Let's first look at wire number 1. We know that the magnetic field is going to wrap around like this. Okay? And what that means is on this side, if the current's going up and you wrap it around, that means on the right side of current 1, it's going into the page or into the screen. Okay? And that means on the other side, if we're just looking at current 1 right now, on the other side, it's wrapping going inside, but then when you wrap all the way around, on the left side, it's going to be coming towards us, going out. So we should already know that. Okay, so on this side, it's coming out. On the right side, it's going in. Okay, so now, next thing that we should know is the distance between the wires, the D, impacts the magnetic field strength and therefore the force exerted. But now let's just look at wire 2. If we look at wire 2, we see, and we're going to use the right hand rule now, not the grip rule, we have a current going up. But there's also a magnetic field that's going inside the screen like this. So that means that there's going to be a force that's going to the left. So wire number 1 is creating a magnetic field. That field is going to be exerting a force that's going to the left. Okay? Now, if we erase a lot of this, and now we look at wire number 2, it's going to be a little bit different. Now, we're going to switch it and see how things are going. Okay. So, wire number 2, we're just looking at wire number 2 now, is making this magnetic field. On the right side of it, it is going inside, and on the left side of it, it is going outside the screen. So it's going to look like this. Now we're just looking at wire number 2. Okay. And on this side, it's going inside. Okay. Now, if we look at wire number 1, we see we're going to use the right hand rule. We're going straight up. That's where the current is going. And then we know that the magnetic field is going out towards us. So this magnetic field is coming towards us. This magnetic field is generated from wire 2. So now we know that the force it's going to be going is to the right. So what's happening is these two wires that have the current are both creating magnetic fields, and these magnetic fields are having them go toward each other. Okay, there's a force kind of having them go toward each other. Okay, and what's the force that's doing it, or what's the amount, the magnitude? Here's the formula for that. This is the mu 0, current 1 times current 2, the length of the wire, times 2 pi d. This mu 0, we call this the permeability of space, which just means that it is the medium that we're working through, which we're just saying is a vacuum. Okay, and that medium of the vacuum is 4 pi times 10 to the power of negative 7. Okay, no units or anything like that. All right, moving on. Let's observe how wire number 1 exerts a force on wire number 2. We kind of already talked about this, but I'm going to go through it again just because I do feel like it was probably confusing. So using the right hand grip rule for current 1, we can see that the electric field produced where wire number 2 will be inside the screen. Okay, it's going inside the screen on the right side of wire number 1. Okay, right side. Okay. Using the right-hand rule for wire number 2 and knowing the electric field is pointed inward from current number 1, we know that wire number 2 will feel a force to the left from the current number 1. So again, I'm going to show this right-hand rule, current going straight up. The magnetic field is pointed inwards. The force is going to be going to the left. Okay? And a quick thing to just know is that if there are two wires going and the current's going in the same direction, they will be attracted to each other. The forces will attract to each other. But if the currents are going in different directions, that means the force is going to be a repelling force. They're going to be forced away from each other. Okay? Something quick. We'll talk more about that a little bit later. But let's do some problems. Okay, example number 4, two parallel wires. Wire number 1 is above wire number 2. Both wires have currents that are moving to the right. Which direction will be the force that wire number 1 feels from wire number 2? Okay, so we want to know what the force is on this wire. And like I said, a little hack is if they're going in the same direction, that means they're going to be going toward each other. Okay, so that means for wire number 1, it's going to be going down. But let's just kind of let's just see how it looks. So wire number 2, let's look at wire number 2 for a second. Current's going this way. Oh wait, no, we're going to do the grip rule. So the current's going this way. And that means that for here, it's going outside the loop, right? So everything is going outside the loop on top of it. Outside, so it's coming toward us. Oops. So, okay, everything is outside. And then on this side, everything is going inside. Okay, so now let's do the right-hand rule for wire number 1. Wire number 1 is going this way. It's going outside the loop, so it's pointed this way, it's moving this way. And then the thumb is going to be going down. And like that's what we said earlier, it's going to be down. All right, moving on. A little demo, just kind of showing the force between these wires. All right, here let's do, I think, some calculations. What is the magnitude and direction of the magnetic force between wire number 1 and wire number 2? Two parallel wires, 0.25 meters long and 0.06 meters apart. If each carries a current of 35 amps in the opposite direction as shown in the diagram, find the force and direction on each wire. Alright, so let's just do the mathematical example for this. So we know the force on each wire, the magnitude of it is going to be the permeability of the space, current 1, current 2, times the length of the wires, 2 pi, times the distance between these wires. So let's just write them out. Mu, we know that, it's going to be 4 pi times 10 to the negative 7. The current of both wires, I believe, is 35 amps. 35. The length of the wires, 0.25 meters. And this is going to be equal to 2 pi times the distance they are from each other, which is 0.06. Okay, kind of a lot to put in my calculator, but let's do it. I'm going to get rid of this pi because those cancel out. All right, here we go. 4 times 10 to the power of negative 7 times 35 times 0.25 divided by parentheses 2 times 0.06 parentheses. And then I get the force, which I get is equal to 0.00102 newtons. So I'm going to put it as 1.02 times 10 to the negative 3 newtons. And remember, they're going in opposite direction. The current of the first one is going up, the current of the second one is going down. So that means they're going to be repelling each other. So that means this force is going to be going to the left of wire 1, and for wire 2, it's going to go to the right. And I guess I'll show the proof of that for one of them, but I don't want to do it for both of them. So let's look at wire number 1. Wire number 1 is creating this magnetic field going this way. So on the right side of it, it's going into the page. So into the page. Now, if we look at the wire number 2, the current's going here. We're doing the right-hand rule. It's going into the page, so we're going like this. And that means it's going to the right. And then the other one is going to be the same. But anyway, opposite directions, they're going to go opposite ways. Okay? All right, moving on. Two parallel wires of the same length carry currents of 7.5 amps and 4.0 amps. They are separated by a distance of 0.15 meters and experience a force of attracting each other with a magnitude of 2.5 times 10 to the negative 4 newtons. What is the length of each wire? Okay, great. Let's write some things. So they're attracting each other, so that means they're both going in the same direction. So I'm going to say 7.5 amps. This one is 4.0 amps. The distance is 0.15 meters. And we want to find the length of these. Oops. Sorry, losing a little bit of space. And then the force of attraction that they feel is 2.5 times 10 to the negative 4 newtons. Okay, so let's write this all down. Force is equal to mu 1, 2 length divided by 2 pi distance. Okay, now we're looking for length. So there's going to be length is equal to force 2 pi distance divided by mu naught I1 I2 length. Okay, now let's do it again. The force is equal to 2.5 times 10 to the negative 4. 2 pi. The distance is 0.15. And then this is going to be equal to 4 pi times 10 to the negative 7 times 7.5 times 4.0 times the, nope, oops, not times the length over here, just that. Okay. And that should help us find it. Okay, so let me plug this on. Let me cancel out the pi's because I feel like that just makes things confusing in the calculator. So 2.5 times 10 to the power of negative 4 times 0.15 divided by double parentheses 4 times 10 to the power of negative 7 parentheses 7.5 4.0. So that's going to give us an answer of 6.25 meters. Okay, are the currents going in the same direction or opposite direction? Again, since they are attracted to each other, that means they should be going in the same. They're going in the opposite directions, but they are attracted to each other. Okay. Oh, sorry. The currents are going in the same direction. All confused. All right, great. Since they're attracted to each other. All right, so that's pretty much it. Next time we're going to be talking a little bit more about electromagnetic induction. So hope to see you guys with that one. Bye, everyone.